I'm Antonio Sala, and in this video we are continuing the case study of manipulated variable and controlled variable selection. In this case, we will discuss how to assess validity of such a selection for disturbance rejection tasks. In particular, we will achieve complete disturbance rejection, so my manipulated variable increments must exactly cancel out the effect of disturbances on the output. We'll have this model as the linearization on this operating point. This will be G and H transfer functions, and in this video we will just restrict to the DC gain steady state disturbance rejection. These are our limits in the incremental manipulated variables, non-symmetrical, and in our disturbance rejection problem, we will assume that disturbances in absolute units, non-incremental, lie in these intervals around this operating point, so that the incremental displacements of the disturbances will be in the range from 0.8 to minus 0.6 in the first disturbances, and the second disturbance will range from minus 0.65 to plus 0.4. So, if we first start with the geometry of ellipses, we must scale such geometry to transform to the geometry of the spheres in order to apply singular value techniques. So, as our singular value computations will assume that everything is symmetric, we need to choose the worst case disturbance as the scaling factor. So, we'll choose 0.8 and 0.65 as the smallest symmetric interval around the origin that comprises the actual increments. So we are on the conservative side of things. This is the disturbance scaling. And then if we recall input and output scaling, the worst case input will be the lowest increment available, scaling matrix with 2, 0.5 and 3 as input scaling. Here I have it. And then regarding output scaling, intuitively, if we want the output to be 0 when a disturbance is cancelled by my control system, then speaking about output scaling is nonsense. And indeed, whatever the output scaling we use for our scaled gain matrices, the results will be the same. So EU is important, but not so EY. But okay, as we chose this output scaling matrix in our setpoint tracking discussions, we'll just keep the same output scaling, because in such a way the scaled gain from manipulated variables to controlled variables will be exactly the same that we already computed and discussed in previous videos. But again, the choice of output scaling is not relevant because we do want output increments to be 0, so 0 can be scaled by anything and it's still 0. But well, if we keep that output scaling, then this will be the gain of G and the disturbance effect scaled to the same output units when subject to scaled input variables, in this case scaled disturbances. Well, then H scaled will be this H gain-esque. So, how do we address total disturbance rejection? Well, the basic idea is that the increments of output due to GU must be equal but with opposite sign to those caused by HD. So, this feed-forward transfer function will be the one that would compute the needed input, but if G is not square, then we are lucky, we have infinite solutions, so we will produce the one with minimum norm of U using a pseudo-inverse, and of course pseudo-inverse over the scaled units, so that all inputs have the same technical meaning. So this means that this computation computes the feed-forward element that if disturbances were measurable, we could directly implement to cancel their effect. Inputs to this feed-forward matrix are the two measured disturbances, and outputs are the 3 inputs in scaled units. So we are assuming that disturbances range in the unit circle, 2-dimensional, in the SVD geometry, and the inputs must not get out of the unit sphere in 3D geometry with these scaled units. Of course, the value of the input needed to cancel the disturbance is the same whether we are able or not to measure it. So we are not discussing how we'll be able to cancel the disturbance. Maybe we will do it with some, integral action controllers or whatever. But the thing is that the equilibrium value to cancel them is given by U equal this feedforward matrix times the actual value of the disturbances. So, well, if disturbances are in the unit sphere, when multiplied by this matrix, then the output ellipse in input space will be something in the 3D world, 2-dimensionals, because the disturbances are 2D, but it will be some ellipse rotated in whatever direction. The thing is that the maximum gain of this feedforward matrix is 0.55, so that means that when disturbances sweep the unit circle, the needed inputs to cancel them will at most have a norm in scaled units of 0.55, so they will not saturate. So this is it. The easy way is with this one-liner. After the scaling, we can say that disturbance rejection problem we are posing is feasible in the geometry of spheres, at least. In fact, we have sort of almost a factor of 2 of extra disturbance increments that could be cancelled. More on that later. The thing is that, this SVD is the only thing I would ask in a pen and paper examination to my students, but as we have Matlab, then we can draw these things. But the thing is that input space is 3D, so drawing things in 3D is kind of more complicated, and in order to see them, I must rotate the perspective or whatever, so we will draw things in output space. How? Well, in earlier videos, we drew this red ellipse, which was the reachable output with unit sphere inputs in scaled units. And that ellipse was drawn by computing this gain transposed matrix, and then using that thing to draw this boundary curve denoting the limits of the reachable output space. That was this red ellipse, and now we'll keep the same M matrix and we'll do the same computations with a disturbance H gain scaled matrix, so with this MD. And this ellipse drawing, we will draw the output increments that may be achieved when disturbances ranged in the unit circle. So here is what we have. The red ellipse I showed previously in previous videos, now in here it's blue, sorry for the color change. And then the swept ellipse in output space, swept by unit norm disturbances, is the yellow one. So as the blue ellipse, equal to the one in previous videos, is larger than the yellow one, it means that a suitable choice of inputs can of course compensate the output values in the yellow ellipse. And in fact, if I zoom in the blue ellipse, multiplying it by 0.55, then I get this 0.55 associated to this minimum gain, putting it there. With this line, I draw a dashed ellipse with a size 55% that of the larger reachable space. So we geometrically confirm the concept of the maximum gain, saying that the sphere of radius 0.55, when multiplied by the DC gain, sweeps the red dashed ellipse in the output space, so that it can cancel, of course, any output increment due to disturbances in the yellow ellipse. So this is how we understand the meaning of SVD in the geometry of ellipses. Let us now address the same problem in the exact polyhedron geometry. I'll have a zoom factor here that now I leave it to 1 because we wish to understand in the same way that we have this 0.55 minimum gain in SVD. We now wish to understand how much we can expand disturbances or whatever while keeping feasibility, but that will be at the end. Now the disturbances will range in a rectangle in disturbance space with these vertices, and the way to check whether there exists a U in my required upper and lower bounds for it that cancels the disturbance will be with quadprog. In here I have the lower bound, in here I have the upper bound, and in here I am saying that G times U must be equal to minus H, in this again of course, times each of the vertices of the disturbances. So if I can cancel extreme disturbances without saturation, I will be able to cancel non-extreme ones also without saturation. So these are the equality constraints, and then I can minimize whatever I wish. But for the actual numerical results to be coincident with the pseudo-inverse scaled stuff we did in the SVD, then I am minimizing the square of U scaled, which is of course this thing in absolute units because gain G and H has been put in absolute units, as well as input lower and upper bounds. So if I am not using scaled units in part of the command, then I am forced to also not use scaled units in the first argument. So I need to express my cost index like this. But anyway, whatever stuff, as long as it's non-singular, I put there, feasibility or not feasibility will be exactly the same result from Matlab. So in this case, as it obtains a minimum found that satisfies those constraints for every extreme disturbances, then of course the problem is feasible and we can cancel the disturbances even with the geometry of the rectangles. Then what is the equivalent of the SVD maximum gain stuff in polyhedra? Well, we can check that if we multiply our disturbance size by 1.78, or well, it would be the same that multiplying our input size by 0.56, then we get this zoom factor giving us the same information as the maximum gain in the SVD. So we have a margin of 78% of disturbance increase or 56% actuator power shrinking, and the problem will still be feasible, minimum, it's all feasibles, but if I zoom a little bit more, then we have here some stuff telling that, one of the vertices was infeasible. Matlab couldn't obtain an input in the valid 3D prism that cancels the effect of such a large disturbance. Well, so this is it. Nevertheless, I will execute again with zoom factor 1, and now if you analyze this code, I put the extreme disturbances times the DC gain matrix to get the image vertices, and then I plot that polyhedron in cyan and the reachable polyhedron in output space in green with the manipulated variables. So here we have this stuff, and of course, as the red thing is larger than the cyan one, then we can cancel those output increments. I change sign here because, my input must compensate the output increments with opposite sign. The thing is that if I zoom out this extra 78%, then the cyan thing touches the edge of the green reachable output polyhedron with valid inputs, and so if I make the cyan polygon larger, then it will render not feasible. So this is the geometric interpretation of what we did with quadratic programming. Back to zoom factor 1, we can superimpose in scaled units the ellipses and the polyhedra to compare. I am not detailing all this code because, it would take me too long and make this video already more boring than it is maybe. So you can pause it and examine it carefully, or just download from the materials in the description. The thing is that the important thing is understanding this. In scale units, the red and cyan are the same as before. The reachable output with manipulated variables U, green, and reachable output values by disturbances, so green is larger. Good. So now, if I zoom in, we'll concentrate on this part. Then the cyan thing is the actual reachable set, but if we do a worst case symmetric unit square in disturbances in scale units, then the worst case stuff is a bit larger, and the ellipse we see here is somehow the reachable output values with inputs in the unit sphere. So you see the difference between the unit square versus the unit sphere, and the non-symmetrical smaller square in cyan. Unit square in dashed contour, unit sphere mapped to output this violet ellipse, and non-symmetric smaller rectangle in cyan. And then the ellipse, we obtained the reachable ellipse with unit sphere manipulated inputs is the yellow one, so it's larger than the violet ellipse. And the dashed polygon here is the set of outputs that can be swept with the smallest conservative unit square input from the scaling. My input range is non-symmetric, is larger, the solid green, but the scaled SVD approach somehow approximates the image of the cube in input space with vertices in plus minus 1, and the yellow ellipse is somehow tangent to them. So with this superposition of the ellipse and polyhedron geometry results, you may better understand what we are doing in each of the cases. So with this we'll end the video here. Thanks for watching.